through our whole lives, we spend it learning about new things and understanding their functionality. But some things are more complex to understand than others, and some things are inexplicable. But black holes belong to both of these categories. They are complex and they are inexplicable. But why are they like this if they have been theorized for over 100 years? Well, scientists still have questions that haven't been answered, such as what happens to the things that go inside a black hole. For scientists, the obvious answer relies on the point between quantum mechanics and general relativity. But the problem is that the complex and intricate mathematics of both theories lead to contradictions within both. And one of these is called the information paradox. To begin understanding this paradox, we first need to understand what a black hole is. Imagine a basketball filled with pressurized air. The internal pressure of the basketball prevents the atmosphere from crushing it. But if this internal pressure drops, then the atmosphere will crush the basketball. Something similar happens to stars. Inside a star, a process called nuclear fusion takes place. In this process, hydrogen atoms combine with other hydrogen atoms to make helium, and all this way around until they make iron. This process generates energy for all elements lighter than iron, but for elements heavier than iron, it consumes energy. If this energy is liberated, the star can balance its internal pressure with the force of gravity from outside. So when the core reaches iron, it can't fuse anymore. The star runs out of gas. So the balance is broken and gravity crushes the star. The star implodes, and then all of that energy is released in a massive explosion we call a supernova explosion. Supernova explosions usually leave remnants, clouds of gas that will in time form other stars or other planets. But if the star was massive enough, the remnant would be a black hole.
Now, let's start with what black holes actually are. Black holes are objects that have an immense gravitational field. This gravity is so strong that not even the fastest thing in the universe can escape from it, and that is light. And since light cannot escape from the black hole, we cannot see what's in the center of the black hole. But black holes are not just the vacuum cleaners of the universe that suck in everything that comes across the path. No, you can actually escape from a black hole if you're outside the event horizon. The event horizon is the edge of the black hole itself and the point where you can still escape from it, as I have said before. But near the event horizon is also a limit where time and space are greatly modified because of the gravitational pull. Here you could see as time really changes, because if someone sees you go inside the black hole, you would only stop and he would see how you turn to red and only disappear. But in the hypothetical case that if you went inside the black hole and you did not suffer an instant death, then you would only see everything going fast forward. You are inside the black hole and see everything around you fast forward motion. Now, black holes were first studied with relativity, but Stephen Hawking, after the mid around 20th century, started using quantum. What did he discover as quantum? Was that in reality black holes lose mass and irradiate energy. How is this possible? Well, this is because of a weird phenomenon. The particle and antiparticle pair that come out of nowhere. Nowhere because out of nowhere. These are virtual particles. They are called virtual particles because they exist and do not exist at the same time. Why is this? Because they appear out of nowhere. The energy necessary for them to exist eliminates itself because they collide and destroy each other. But what happens if one of these particles appear near the event horizon? One would be sucked into the black hole and the remnant would be needed to become a real particle. Where does the energy required to become a real particle come from? Well, it comes from the black hole itself. And then in time, the black hole will lose energy because of these particle and antiparticle pairs. And soon enough, it will disappear.
Now, what happens to everything that goes inside a black hole? We know that it all gets into its fundamental bits, the building bricks of reality. But we don't know what happens later. When we combine general relativity and quantum theory, we get a surprise. A welcome one for sure, because it says that we need more science because we don't understand what's happening. But to go on, we need to understand a concept which is information. When we think about information, we think about knowledge itself, or a text, or a book. But in physics, you need to go to another level. In physics, information means the way that atoms are arranged to build different things. For example, you can build a cheese, or a rat, or a boot. It's all information.
Now, information has a core principle involving quantum mechanics. What is this principle? Well, it explains that no matter what you do to the object that you have in your hands, the information stays as it is. There is no way to make it disappear or have it lost. Now, if you have trouble in understanding this, imagine the law of conservation of matter and energy. Here we can see that no matter what happens, it stays, and we have no participation in this. After this, we want to try to understand information, but unfortunately there is no way that we can understand it because we can't measure it or observe it directly. However, if we had a way to analyze it more deeply, we could rebuild anything that we would want to, including dinosaurs, for example. Now we have understood information, we can talk about topics related to information. The first one we can see is quantum determinism. And determinism usually is explained as figuring something, the position of something after we analyze its first characteristics. But in quantum physics, this is not so simple. We were fortunate enough to interview Ken Caesar, who answered in a simple way what quantum determinism is. Ken Caesar explained, well, particles have a wave function that explains the probability of finding that particle in a specific place in a specific time. But we cannot know for certain because of the uncertainty principle. This principle explains that we cannot know the momentum and the position of the particle at the same time. Think about the electron cloud model. This model explains to us the possibility of finding an electron in a certain place, but it does not explain where it is exactly. So in a sense, particles are waves, and we can use the double slit experiment to explain the behavior these waves have. We use sound waves. Because of diffraction in double slit experiment, there are certain places where the waves will cancel out each other in a certain place and amplify each other in a certain place. You can have the same effect using particles, but this is due because of the uncertainty principle of not knowing where the particle will be at a specific time and a specific place. So in other words, the quantum world is not deterministic, but the probabilities expressed in the wave function for each particle is determined, and this is information for each particle. Well, we can modify the wave function with operators, but just as 2x and 3x are different, x is always the same.
Now there's another concept we need to understand. Its name is reversibility. Imagine you just build your 5,000 Lego masterpiece and you drop it. You will feel bad for sure, but you can grab every single piece and rebuild the whole structure once again. It works the same way for more complex things. The usual example is burning a sheet of paper. If you burn it, it will turn into ash. But if you grab the ash, the heat, and the light released, you could theoretically rebuild the piece of paper. Now this is where it gets spooky. For black holes there is something called the no-hair theorem. This theorem says that you can only measure for a black hole its mass, its electric charge, and its angular momentum. Now, scientists expected that Hawking radiation had nothing to do with the contents inside the black hole, so there was no problem. But this is where mathematics comes in, so you just have to trust us. When scientists did the math, they realized that if the materials that come inside the black hole are in a pure quantum state, they would need to undergo a transformation to a mixed quantum state when they get out of Hawking radiation. And this is not possible because this mathematically would require loss of information, and this violates reversibility.
And here's the problem. With our current understanding, there seems to be something we are missing. Information is lost, but information cannot be lost. For this, some solutions were given to the public by scientists. The first one is that information is lost. It's all very nice and good, but if we accept this as true, then everything we have done in science since the beginning of humankind is wrong. So, it's not so nice indeed. The second solution would be that information is leaked out of the black hole media the Hawking radiation emitted. However, this one has also a problem. Nothing can escape a black hole once it has entered the event horizon. And to solve this problem, they came that information is leaked out of the black hole when it's near the end of its lifetime. This would imply that all the information goes back into the universe all at once. These are some explanations given that information is leaked. However, some explanations say that there is a remnant after a black hole has evaporated. The first one would be that information is put in a remnant, but in a very small space. Very, very small. The smallest it could ever be. This is the Planck length. The Planck length is 1.6 times 10 to the minus 35 meters. That is 34 zeros to the left. It is extremely small, and this is why this solution would require an infinite amount of remnants in order to contain all the information. However, the second solution with remnants implies that there is a huge, humongous remnant that contains all the information, and this is only one. There's a third unique solution that contains that all the information that was inside the black hole goes to a new baby universe created by a black hole. This is interesting because maybe this is how Big Bang was made.
There is one last explanation, and this is by far the most interesting, frightening, and one that actually solves the paradox. It concerns the holographic principle. This principle says that three-dimensional space can be encoded into a two-dimensional surface. For a black hole, this means that everything that goes inside, its surface increases. So maybe the information that all the things that go inside of the black hole are stored in some way in the surface, like using the holographic principle. So when the Hawking radiation emits, the black hole loses mass and the surface gets smaller. So the information stored on the surface gets carried out back to the universe. There's a problem though. We have never seen Hawking radiation, and it would be necessary to see it to confirm the theory. Now, the holographic principle implies something else. That if a black hole can do this, then any surface can store information in this way. And in this way, the universe is a hologram. But we don't really know. this is a very recent field and there is much to do because we don't really understand it. In Latin, omne ignotum pro magnifico means everything unknown is grand. And though the original context of the phrase means that we exaggerate too much about the difficulty of things, that is the reality. We don't understand many things because they truly are difficult to understand. And for black holes, we may never understand them. There might never be a solution to all of these problems. Maybe someday a very visionary scientist will come up with a great solution that will reconcile quantum theory and relativity into a theory of everything. But we can only hope. Until that time, the unknown is truly grand.
Thank you. It's over.